This is our most negative energy, because this, remember, is where the electrons are closest to the nucleus. This could be called the ground state. This is the closest they can get. They can't get any closer to this. So it's the most negative. Remember, a very negative number is good, because that's a very small number. So that's where the electrons want to be. And then these electrons are getting bigger and bigger. A smaller negative number is really a bigger number. So the electron is less and less happy. What does it mean if you get all the way to infinity? It means that you've ionized the electron. It means that you've actually removed it from the atom. If you put in enough energy to get all the way up to here, the electron has actually been removed from the atom. So how much energy would it take? Say we start with an electron over here. How much energy would it take to ionize this atom? 13.6 electron volts. That's right. If you put in 13.6 electron volts, the electron will get to here. Good. What would happen if we put in, say, 14 electron volts? Well, what would happen is this enough to ionize it? Yeah. And then there will still be 0.4 electron volts left over for kinetic energy. So if you put in 14 electron volts, you'll end up with an electron that has 0.4 volts of kinetic energy and has been freed from the atom.
So you eject the electron? You
eject the electron, and it's moving with a speed that corresponds to 0.4 electron volts of kinetic energy. Whereas if you only put in the 13.6 electron volts, then the electron just barely gets out of the atom. It doesn't have any kinetic energy left over, so it's kind of just sitting there in the limit, basically. So you would never put in exactly 13.6 electron volts. If you put in a little bit more than 13.6 electron volts, it just barely gets out and has a very small amount of kinetic energy.
So I remember something from chemistry that you have to put in the exact right amount of energy to get from, so that's to get from like between n equals 1 and n equals 2.
Right.
But just to eject, you can go over.
That's a good point. So are these energies inside the atom quantized? Yeah, they only take on certain values. Something I didn't mention is once the electron is free, its energy is continuous. Once the electron is free, it can take on any energy. So we've been talking about how things are quantized in modern physics, but I might have given the wrong impression that everything is quantized. Energy is not always quantized. Generally, the energy of confined particles is quantized. But if something is free and not confined, its energy can be continuous. So in our diagram, once you get to positive energies that are outside of the atom, we should just have everything shaded in. All of these energy levels are now possible. It's only while the electron is confined within the atom that its energy is quantized and it can only take on certain values. So if you're going to ionize the atom, you can put in any amount of energy you want, and any extra energy will just get translated into kinetic energy. But while we're moving around inside the atom, the energy is definitely quantized, and only certain levels are possible.
So only if you put in, like to go from n equals 1 to n equals 2, you have to put in the difference between 13.6 and 3.4.
Exactly, you have to put in 10.2 electron volts.
So if you put 10.3, you don't go anywhere?
Yeah, nothing happens. You have to put in the exact right amount of energy or nothing happens. This is, again, a surprising prediction of this modern physics. The normal, so the common sense view is that if you put in some energy, the electron will get further from the nucleus. But it turns out that because the energy levels are quantized, you have to put in the exact right amount of the energy to move it exactly between two of these levels. It can only absorb energy in these increments.
So what happens to energy? It's just not absorbed?
It just wouldn't be absorbed. That's right. So the energy would probably be coming in with a photon, right? We're shooting photons here. Well, some of the photons will be absorbed by the electrons, and some of the photons will just shoot straight through and not be absorbed. Well, any photon that does not correspond to an energy transition cannot possibly be absorbed. So it's just going to shoot straight through and not be absorbed. Only the electrons that correspond, I hope I said that correctly, only the photons that correspond to a precise energy transition can be absorbed. The other photons can't possibly be absorbed because of the quantization.
I remember that because at my Chem 1 AJSI, he made a good analogy with it, that the energy levels are like when you play Mario, and you're jumping from like pipe to pipe, like if you land right in front of like the pipe that you're jumping on, then you just fall down and nothing happens. Or if you jump over it, nothing happens, but if you jump exactly on it until the next one.
That sounds like a good analogy. I never played Mario, but that sounds like a good analogy. So what he's basically saying is close is not good enough.
You have to jump exactly.
Yeah, you got to get it exactly right, or you don't, or it doesn't, or you don't get the transition
So
at all.
if you jump past it, you don't somehow get
Right.
put back on it.
Exactly. Yeah, it would seem like common sense would say that if you jump past this, you just fall back down onto it. But that would say that you can absorb continuous levels of energy, where it's really quantized. All right, that's a pretty good analogy. Maybe I should play more Mario. All right. Okay, so yeah, let's say that we want to move this electron from n equals 1 to n equals 2. First of all, how is it going to do that? Is it going to do that by absorbing a photon or emitting a photon?
Absorb it.
Because it needs to get that energy. Remember, the energy is being delivered by photons. One thing that tends to confuse people here is here we have a problem that involves both electrons and photons. The electron is living inside these energy levels, and the photons are the things that can bring energy in or take energy away.
Also, when it emits a photon, it emits light. That's the energy it's getting out of it.
That's right. Good.
Okay. So electron, you want to go from 1 to 3. So you need to put.
Oh, yeah, I was going to do 1 to 2, but we can do 1 to 3. That's fine.
That's okay.
1 to 3. So how can we figure out what type of photon would work there? I don't know if I want to work through all the math there, but what calculations would you do?
So you have to find 10.2 is the energy.
Good. So the change in energy is 10.2 electron volts. We don't really have to care about the signs here. You can just subtract 13.6 minus 1.5 and you get the right magnitude of the change in energy. So we need 10.2 electron. Is this right? 10.2?
Yeah, I did 13.6 minus 3.
Oh, you went back to n equals 2. Let's go back to here. Sorry, I keep changing my mind.
So 13.6 minus 1.5.
Yeah.
So it's 12.1.
12.1 electron volts. Right. So how can we figure out what type of photon we would need to send in to accomplish this?
Oh, like what? What type? You mean like what wavelength?
Yeah.
Oh, so you choose that.
Yeah. So let's just talk that through.
So you have, and you're using, so you have E, you have the E, so then E times, so you can find the F
By good.
by dividing H,
Good.
and then,
Now, however, this is in electron volts, so
uh,
we'd have to convert into joules. We won't actually do that right now, but since our value for H is in joules, we'd have to do a unit conversion there. So that's a unit conversion that comes up a lot. We can't use these flowcharts in electron volts,
so then you use E equals HF
right?
to get F, and then use C equals F lambda to get the lambda
Right? And that would basically tell us what type of photon we're shooting at.
photon.
Or we might have stopped here and said what type of frequency we're shooting in. So as we were talking about, only certain frequencies and wavelengths will be absorbed by this atom. And here's how we can figure out what frequencies and wavelengths would be absorbed. So this is a very standard type of problem. I'm pretty sure to see. There's in the homework and in the exams. Okay. How about if the electron, what happens when the electron falls back down from here to here? What's going to happen photon-wise?
It's a photon of that.
Yeah, and if we hadn't already figured it out, we could figure out what wavelength and frequency was being emitted by going through that same process. So again, it's kind of pointless to focus on the signs here. All you have to do is figure out the magnitude of the energy change, and that magnitude of the energy change will allow you to find the frequency and the lambda over here. All right. So I don't think we've had much occasion to use this upper flow chart for solving problems today. So this is a good example of when we would use the upper flow chart. Why are we using the upper flow chart even though this is about an electron? Well, because even though it's about an electron, it's also about a photon, and we want to know what's the wavelength or frequency of the photon that's being absorbed or emitted. So you have to be careful in these problems because there'll be both electrons and photons, so you have to know which of these flowcharts you're using. But if we want to know what type of photon is being absorbed or emitted, you have to use the top flowchart. So the key thing is, in this type of setup, it's the photons that are bringing energy in or taking energy out. You can think of the photons as just energy carriers. They bring the energy in that allows us to promote an electron to a higher energy level, or they take the energy out when the electron relaxes to a lower energy level. And then we can use that energy and this top flowchart to find what type of photon we're talking about.